In this video, we're going to discuss bounded monotonic sequences and the theorem that describes how they converge. A bounded sequence is a term that we use to describe a sequence where we've sandwiched every single value of that sequence in between two different numbers. So the image I like to keep in mind for this is the following. So first of all, we can talk about the case of bounded above. So if we say a sequence is bounded above, then what we're talking about is we imagine there's some number m, and if I plot out every single term of this sequence, whatever they're doing, they could be bopping around. It's not a statement that the sequence necessarily converges, but as I go from 1 to 2 to 3 and so on and so forth, and I'm plotting terms of the sequence, every single one stays under some number m. Okay, and it may actually be that every other term bops way down here, but there is some upper bound m. To say it's bounded below is to say that if I look at every term of the sequence, then I have this image. There's some number little m, and when I look at every single term of the sequence, the first one, the second one, so on and so forth, all of them, and like I said again, it doesn't have to be that they don't all have to decrease. That's not required. Just that every single term is bigger than this number m, bigger than or equal to. And when we have a sequence where we can find a full-on upper and lower bound, big M and little m, and every single term of a sub n, all the terms stay between those two bounds, then we call it a bounded sequence. So we're saying that every term of a sub n is trapped in between the same two numbers, little m and big M. Let's look at some examples of sequences and see which ones are bounded. So the first sequence I have here is 1/3 to the n. So this is a geometric sequence whose terms are 1/3, 1/9, 1/27, 1/81st, and so on. Any sequence where every term is positive is naturally bounded below. And I tend to abbreviate bounded with BDD. So if you see that, that's what I mean, bounded. And all positive sequences are bounded below because to say a sequence has all positive terms is to say every single one is greater than or equal to 0. So 1/3 to the n, so that's a fact I'm using, but 1/3 to the nth power is always greater than or equal to 0. So that's its lower bound. That's representing that lower bound m. So it's bounded below. And additionally, I notice that with the sequence 1/3 to the n, every number in the sequence is less than or equal to 1/3. Now, I chose a bound that happened to be the first term, and I noticed all further terms were smaller than that term, but I actually could have chosen any grossly oversized upper bound as well. So while I'm saying an upper bound 1/3 is there, if I hadn't been able to figure out exactly what it was, but I saw that every single term was smaller than or equal to 10, that would equally well tell me that the sequence is bounded above. To state that there's an upper or lower bound to a sequence does not require me to find the best upper or lower bound, but only to find some upper or lower bound. So this is an upper bound, just like 1/3 was. So you notice there are multiple choices, and the key difference between 1/3 versus 10 is that 1/3 is a least upper bound. So there is no number that would be greater than or equal to every term of this particular sequence. The second example, we take 1 and we're always subtracting something from it. Because it's always 1 minus something, it's a little easier to see that an upper bound for the sequence 1 minus 1/n is 1. I'm always taking a little bit away from 1, and therefore 1 must be bigger than or equal to every term. Additionally, I notice that the first term of this is 1 minus 1/1, or 0. The second term is 1 minus 1/2, so 1/2. The third term is 1 minus 1/3, which is 2/3, etc. And so I see that every term of this is positive or non-zero. And therefore, I can use 0 as a lower bound to this sequence. So this is a fully bounded sequence as well. with upper bound 1 and lower bound 0. Next, let's look at the sequence 2 to the n. So this is the sequence 2, 4, 8, 16, and so on. This sequence, every term is positive, so it's bounded below. So the sequence 2 to the n is always greater than or equal to 2. So I do have a lower bound, but notice it is not bounded above. There is no upper bound to this sequence. I can just find a bigger power of 2 to the n. Even if I tried to come up with a number that I claim was the upper bound, if I can always find a power of 2 that will be bigger than it just by, say I said the upper bound was 1 million. So if I said the upper bound was 1 million, well then whatever the logarithm of the log base 2 of 1 million is, that's going to give me a number of my sequence. So if I add 1 to that, then, I round up to the next largest real number, whole number, sorry, then 2 to that power would be bigger than 10 to the 6th, and therefore it wouldn't be an upper bound. So any candidate I would have for an upper bound would not be big enough. The sequence keeps growing without ceasing. The last example I have here is sine of 3n. Now, so we're talking here about sine of 1, sine of 2, sine of 3. As reading measure angles, none of these are even multiples of pi over 2 or anything. So I'm going to get all sorts of different values. Every term of the sine function, no matter what it is, whether it's 3 times an integer or not, will be a number between -1 and 1. So I have this, and knowing that, that's about the best I can do. So this is a fully bounded sequence. But the interesting thing is, unlike the other 2 bounded sequences I've listed, this one will not converge. So I have the following theorem. Convergent sequences are bounded. If I can come up with a sequence that has a limit, so if I have a sequence where I know it has a limit, so you suppose limit as n goes to infinity of a sub n equals some number L, then that tells me I actually can find an upper bound and a lower bound for that sequence. And this has kind of got a cool proof, if you ask me. Okay, so to make it a little more easy to understand the context, let's just suppose the limit of a sub n is 5 instead of saying it's L, just so you can get a sense of how this proof goes. So suppose the limit of a sub n, this sequence, is 5 as n goes to infinity. Then what the theorem says is that for any epsilon, I'm supposed to be able to take the absolute value of a sub n minus that epsilon and find a number after which I'm within that closeness to 5. So why not take that epsilon to be 1? So we're going to let epsilon be 1. Then there is a capital N such that if we take every term of the sequence, a sub n, and we subtract off our limit, then that value is going to be less than 1 whenever n is greater than my capital N. So in particular, dropping the absolute value signs, a way to read this is to say that a sub n will have to land between L minus 1, or sorry, L plus 1 and L minus 1. And L was 5 in our example, right? So let's make these 5s. So I'm really saying that if the closeness is 1, that I can actually make it so that terms after a certain number in the sequence will be between 4 and 6. So I already have a candidate for an upper bound and a candidate for a lower bound. So now what I'm going to do is I'm just going to say, well, if it turns out that terms before this capital N are not that close, because I picked this somewhat arbitrarily, I'm going to let my capital B be the maximum of 6 and every term of the sequence that comes up till my bound, at which point all the terms are bigger than it. So this is a finite number of numbers. One of those numbers therefore has to be the largest, and I'm saying that's the upper bound. And then by the same argument, I can get a lower bound, which would be than less than or equal to every term here by taking the minimum of 4 and whatever the prior terms of that sequence are. So one of the prior terms of the sequence is the smallest value that sequence takes before we get to a sub capital N. And then if that's smaller than 4, then I make that my lower bound. And if 4 is the smallest, I make 4 my lower bound. And now I've shown that this sequence, which I knew had a limit of 5 in my example, has the smallest value or has a value that's it's always bigger than and a value that it's always smaller than. And so I know if a sequence is convergent, there's some sandwich I can put inside of it. And because of that visual that we always had, if we knew the limit, then we're sort of saying eventually all the terms get as close as you want inside the tube. One way to read what we have happening in this theorem is to say that you can set a tube wide enough. There is an epsilon value at which point every term lands within it if it has a limit. That's kind of a neat way of putting it. You can let your epsilon just be really, really big, like 100 maybe. There's some epsilon big enough that it smothers everything. Now, the best way that this particular theorem gets used is in its converse. So it's not that I use the convergent sequences must have bounds on the top and the bottom as a way of saying something about whether a sequence converges, but rather I can use it to determine when a sequence does not converge. So if I can't find bounds on both ends for a sequence, then it has to be divergent. And here's a key example. So the sequence I made up here is like all the terms of the Fibonacci sequence, except I also have them oscillating. So every other term is a negative number. So I mean, even describing this sequence sort of in like with an explicit expression would be very, very tricky because of the way I did it. I guess the n+1 term is -1 to the n times the sum of the absolute value of the two previous terms. Yeah, that is a hideous way of describing something, but that would describe this as the sequence where the first term is 1 and then we have this behavior. I just don't know that that's the best way to describe it, where you would say that the first term is 1 and then the second term is -1, and from there on then this formula would work. But what we can notice is that because every other term is positive, the positive ones are growing ever bigger. So there's no upper bound. The Fibonacci sequence was an example of a sequence that we said diverged. You can always find a real number that is, if you pick a real number there, you can find a term after which every term is bigger than that number. And so that'll be true for the even terms here. Therefore, the even terms are not bounded above, and then the odd terms are not bounded below. There's no lower bound because the odd terms additionally are getting, their magnitude is getting bigger and bigger in the negative direction. And so you've got this sequence that if I were to plot it, beep, like that, like that. So the values of this sequence are spreading out, which tells us that it's going to diverge. It cannot be convergent. So this is a really useful way of establishing divergence. And we'll use this at times. If either I can't identify a lower or upper bound, I just found one that didn't have either. So if either the upper or lower bound can't be found, then that is a sign that the particular sequence in question must diverge.